following structures, or follow structures, the following Lewis diagrams for the following atoms: Sr, Kr, S, and Bi. Okay. Drawing the Lewis structures. So, what is the first thing we need to do? We have the symbol. Now we're going to do what? Locate it on the periodic table. Okay, let's go ahead and do that. Sr number 38, atomic number 38. 38 means that it has 38. No, not valence electrons. 38 means it has 38 protons and 38 electrons, right? Now, because of its position on the table, we look at the column heading for the A columns. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. They tell us how many valence electrons it has. One of the questions that you had was, does the column heading tell you how many electrons are in the? No, because in the B's, those are not the valence electrons. Only the A columns give you the valence electrons, right? So the fact that it's in 3B does not mean that it has 3 valence electrons. But if it's in A column, in the S block, the P block, it's telling you how many valence electrons it has. So Sr, 38, how many valence electrons does it have? Second column has 2 valence electrons. Where are they located? The 5s1 and 2 positions. Okay. So Sr has 2 valence electrons, and we will indicate those by 2 single dots around the symbol. Kr, krypton. Okay. How many valence electrons? 8, right? What's unique about krypton with its other column mates? Noble gas, it's an inert gas. It has a full valence of electrons, right? It's satisfied. It's not looking to react. It has a full 8. And I know that since I'm putting in 4 positions and I've got 8, they're going to be pairs. To make it symmetrical, I'll just go ahead and do that now. And there's a Lewis structure for krypton. Sulfur, atomic number 16. So it has 16 protons, 16 electrons. How many its valence? Okay. It's in the 6A column, so it has 6. They are in the 3rd energy level because they're in the 3rd row. And they occupy 3s1 and 2, 3p, 1, 2, 3, 4. Okay, for a total of 6. We know that we're going to go around plus 2. I'm going to start it with 1, 2, 3, 4, 5, and 6. Bi. I don't know what that is, but where are we going? Okay, 83. Thank you. 83. 83 electrons, 83 protons in the neutral atom. How many valence electrons? Okay, so it is in the 5th column, so 5 valence electrons. What addresses do they occupy? They're going to be in the 6th energy level because it's in the 6th row. S1 and 2. P, 1, 2, and 3. For a total of 5. 1, 2, 3, 4, and 5. Now that's the standard way they taught you in the book. Start at the 3 o'clock, go around to all the coordinates, and then start over again. I said before, you're going to learn very quickly when you're going to have more than 1 in each position and learn to offset them so they're symmetrical. Okay? Another hint for you. And as long as you have them in these pairs and singles in any orientation, it's going to be fine, because later on, when we start doing geometries, you're going to learn some positions that tend to work the best for you. If you end up with something from column 5, I'm fine with, if you start right now, learning that it's the easiest if you start putting the double on top and the 3 around like that. Because in most cases, this is going to be a center hub atom, just like carbon tends to be a hub atom. Column 5 are going to tend to be hub atoms as well, with connecting electrons, that these single electrons that form bonds around it. So the vast majority of the time when you have a column 5 element, it's going to be simpler if you put the double unpaired or the paired unbonded electrons on the top. It just makes it easier in the future. 8's easy, it's perfectly symmetrical. Now, what we could do, these are Lewis structures. These are Lewis structures for also every single element in column 2, column 8, column 6, and column 5A. Right? So if I were to ask you then, since we already know what the Lewis structure for SR is, what's the Lewis structure for calcium? There. What's the Lewis structure for, radon at the bottom there? Right? Oh, it's column 2. It's the same thing. All column 2s are going to look like this. All column 8s are going to be this. So I could put any noble gas except for helium. I could put it in there, and I would have the electron configuration. This is column 6, so I could put oxygen in here, cesium in there. I think that's what that is. But plug them in there, and it's going to be the same electron configuration. In the same way, column 5, so nitrogen goes in there, phosphorus can go in there, they can all go in there, and it has the same electron configuration for column 5A elements. Okay? But again, process, if you're still confused on that, just draw the symbol, start counting up, and put the dots in the coordinates 3, 6, 9, 12. Keep counting up until you have the right number of dots. And you'll be fine in terms of drawing the Lewis structure. Okay? Remember, that's for column 1 through 8A. If you end up in a place where you, let's say, chromium right here. What is my valence electrons going to look like for chromium? I know it's going to be an energy level. Which energy level? 3. Okay, these electrons are in the 3rd energy level. Where are my valence electrons going to be? They're going to be at my 4th energy level, right? Because I've filled 4s1, 4s2, and then I went back to 3d, 1, 2, 3. Okay? So if you end up somewhere in the middle, like for iron here, for those of you that used I for iron on your homework, iron is Fe for ferrous, it's Latin. Okay? So if you end up in a D group over here, your valence electrons are to come from the preceding S's. You're going to have 2 in your valence. Why? Because you have, like, for example, 4s1, 4s2, then 3d1, 3d2. The 4th energy level is your highest energy level. That's where your valence electrons are going to be at. Which is why you can't look at the number on top here and know how many valence electrons you have. Look to the left and find out how many were put into, and if you're in here, it's going to be 2 because of the preceding for the higher energy level. If you make it all the way through here and pop back over the P's, now you're back up filling the same energy level as your S level. So any questions on Lewis structures for the individual elements? Again, atoms are neutral structures. Ions are atoms that have more or less electrons than neutral. So they've gained an electron or lost an electron. I'm reviewing just some things that I saw that was repeatedly in error on the homework last night. Give the chemical formulas for the following molecules. Aluminum oxide. I'm going to start my investigation on the formula for aluminum oxide. What do I have to know first? Let's start by what's their chemical symbols for the parts that make it up. What are the building blocks that make up aluminum oxide? So aluminum, which is symbol is Al, good, and it's oxygen for right now. We're talking about the individual atoms, the individual building blocks that make it up. Now that's another thing too that I stressed, that even though now we've learned what a homonuclear diatomic is, that does not mean that the homonuclear diatomics can only combine in combinations of 2. When they form compounds with other elements, we're breaking the bonds between the 2 oxygens and then rebonding them with something else. Okay, so that doesn't mean that O can only exist as O2, O4, O6, O8. It can exist in any combination as individual atoms. But naturally forming, when oxygen is near other oxygens, they will form oxygen molecules, as will every other homonuclear diatomic. Okay, so aluminum and oxygen make up aluminum oxide. So we've got the symbols down. Next step. We're going to ask a question, right? Do you know what the next question is? Are they metals is going to answer part of the question. Now, the question I ask is, what charge does this element, this atom, want to become when it's ionized? What is the charge of the ion it wants to have? What does aluminum want to become in order to complete the octet rule? Several different ways to think about that. So I'm going to look at aluminum and oxygen and say, what charge does this atom want to become as an ion? Because I have a metal and a nonmetal, right? Aluminum is a metal, oxygen is a nonmetal, so we're talking about an ionic bond. Because it's an ionic bond, it's going to be based on charges of the ions. What charge does each of these atoms want to have as an ion? Go to aluminum, and aluminum is a column 3 element. What charge does aluminum want to have? Right, because it's a metal, right? It's on this side of the jagged line. It wants to act like a metal. It wants to give up 3 rather than trying to gain 5. So it wants to lose 3 electrons, and by losing 3 negatively charged electrons, this atom takes on what charge? 3 plus. It loses 3 negative, and by virtue of losing 3 negatives, it becomes much more positive, right? Think of it. If we get rid of the negative personalities, the personality of the whole class becomes more positive, right? As a whole. Get rid of the negative, you become more positive. Here, getting rid of 3 negatives makes the whole thing 3 positive. Oxygen, on the other hand, is a column 6 nonmetal. Nonmetals want to receive electrons. They want to gain electrons because it's easier for them to gain 2 than to lose 6. Much more favorable for them. So the nonmetal oxygen wants to gain 2 electrons. So by gaining 2 electrons, what would its charge become? Taking on the negatives, you become negative, right? Adding negative people to your crew, you become negative. So you're going to add 2 electrons to the oxygen, it's going to become 2 negative. That's what it would like to become. So in this combination between aluminum and oxygen, aluminum wants to get rid of 3 electrons, oxygen wants to get 2 electrons. They're not a perfect match there, so there's going to be some multiple of each other that we have to organize in order to neutralize the charges. We have to balance positives and negatives so that together it's neutral. Now we have a shorthand way of doing that. Do you remember what the technique is? Yes. Good. We're going to go ahead and, for our technique, we're going to ignore, actually I'm going to write it again so you don't lose track of the fact of what we started with here. We're going to ignore the charges because we know they're opposites. And the way we're going to balance the charges is take the superscripts and make them, transpose them as subscripts. And so this becomes Al2O3. We can go back now and check the charges to make sure it's actually neutral. Okay? So if I have 2 aluminums at 3 positive each, that's going to produce 6 positive. And if I have 3 oxygens at 2 negative each, that's going to equal 6 negatives. The negatives and the positives equal each other. They cancel out my molecule as a neutral charge. Because remember, ionic molecules are formed because of the opposite charges between the ions. Okay? So as aluminum is going by saying, man, I wish I could get rid of these electrons, and oxygen's there saying, man, I wish I could get a couple electrons. They're like, okay, deal. Here's 2. I got 1 more left. Here, let me give that to another oxygen. The oxygen says, that's fine. I need another one. Hey, they pull in another aluminum. The other aluminum gives them 1 electron. Okay, that oxygen's fine. But wait a minute. Now this other aluminum has 2 more electrons. There's another oxygen. Boom, boom. There's 2. So for every 2 aluminum that combined with every 3 oxygen, there's a place for every electron to go. And the charges neutralize. And once those ions have come together like magnets. There's no more charge left, so other oxygens and other aluminums going by, there's no place for them to give or get electrons, and there's no charge for them to be attracted to. Yes, Will? We're going to use these numbers, but then as you look into it, you're going to find it's not the least common multiple, it's the greatest common factor is what you're going to do. Because remember we said in some cases if you got a 2-to-2 charge, like for, it was magnesium oxide was one of the assignments, and they both take on 2. Magnesium wants to have a +2, oxygen wants to have a -2. It would look like it would be Mg2O2. However, the greatest common factor is 2, so you divide by 2 and it becomes MgO rather than Mg2O2 because every one oxygen and every one magnesium neutralize each other. Did that make sense what I just said? Do you want me to draw it on the board? Okay. Okay, so this is our technique of determining the molecular formula given the name for an ionic compound. Second one was calcium sulfide. Elements are calcium, it's calcium, symbol is Ca. Sulfide. The element under consideration is sulfur. Sulfur's ionic name is sulfide. So sulfur is S. Ask the question, what charge does this element want to become as an ion? Because we have a metal and a non-metal, agree? Okay, so it's ionic. Calcium wants to take on a 2 positive. Sulfur wants to take on a, okay, because it's column 6. Yep. So 2 negative. This is the case I just talked about. Technique would tell you to say, okay, I ignore the charges and transpose as subscripts. It would give me Ca2S2. But they have common factors. The greatest common factor is 2. So I'm going to divide both of them by 2, and it becomes Ca1S1. Okay, because we're looking here at the greatest common factor. Over here, what's the greatest common factor between 2 and 3? No, that's the least common multiple. Greatest common factor is 1. 2 divided by 1 is 2. 3 divided by 1 is 3, so we're good. Over here, the greatest common factor is 2. 2 divided by 2 is 1. If you think about it in terms of the charges, if I have one calcium at 2 plus and 1 sulfur at 2 minus, those individuals are going to come together and neutralize. I don't need 2 and 2, I only need 1 and 1 because the charges will neutralize. That's why I look at this and say, what's the greatest common factor? 2, and do the division. Yes, sir? Calcium right here in the second column. Okay, so its valence is in the 4th energy level, the 4s1 and the 4s2 position. That's its highest energy level electrons in the 4s1 and 2. So it has 2 valence, meaning 2 electrons in its outermost orbital, highest energy level. So it's trying to get rid of the 2. S over here is a column 6 element, 6a. It has 6 valence electrons. It wants to go get 2 more, so it has 8 to complete the octet rule. The nonmetals over here want to get electrons. This side of the jagged line, they want to get. The metals on this side want to give electrons. So getting electrons, giving electrons. Wants to give 2, wants to get 2. Hey, we got 1 of each. Takes the 2, gives it to the other. They both now have their octets full, but they're oppositely charged and equally charged. They come together. They neutralize each other. Nobody else is attracted. No more places for electrons to come. No more extra electrons to give. The reaction stops. Okay? Beryllium carbide. I'm not going to write it up there, but beryllium is a column 2, right by lithium, right on the top there. Beryllium. Now, Dylan, because it's Beryllium, the same logic of calcium, right? It's in column 2, so it has 2 valence electrons. That is in the 2s1 and 2 positions. So beryllium wants to give up those 2 because it's a metal, which would make it 2 positive as the ideal ion for beryllium. Beryllium sulfide, sulfur, is my, they were both sulfides, oh, carbide, excuse me, carbide. What is the element whose ionic name is carbide? Carbon, right? So carbon is a C. Carbon is also a column 4 non-metal. So it wants to get 4 more. Become 4 negative. Everybody agree so far? Okay. And beryllium's a metal, carbon's a non-metal, so we're talking ionic. So we're good there. We need to make sure that's the case because if it's covalent, these rules don't really work the same. It's got to be an ionic bond to do this. So by technique, ignore the charges, change the subscripts, transpose them. Beryllium 4, carbon 2. What's my greatest common factor between 4 and 2? 2. I'm going to divide them both by 2, and it becomes Be2C. Let's check it with the charges. Beryllium, 2 berylliums at 2 positive each gives me a charge of 4 positive. And 1 carbon at a charge of 4 negative each gives me 4 negative. Equal but opposite charges. Checks. So it's Be2C, beryllium carbide. And lastly, potassium nitride. Potassium, atomic symbol of somebody from the crew. Oh, you're part of the crew? Okay, good. Potassium is K. Just checking. You identified as the group, part of the crew. Potassium nitride. Nitride is the IDE name for nitrogen. So potassium wants to have what charge as the ion? Positive 1. It's a column 1 metal. Wants to go 1 positive, get rid of 1 electron. Nitrogen is a column 5 element, column 5 non-metal, so it wants to become 3 negative. But we are talking a metal and a non-metal. We're good. By technique, K3N. Greatest common factor is 1, so we're good. Charges, 3 at 1 plus gives me plus 3. 1 at 3 negative gives me minus 3. Equal opposite, we're done. Okay. The next question gets into elements with D shells, right? So we have to have specific information. Remember what we said about those elements that reside within the D block is that the ions that they form, they have multiple ions that they can form. So for me to tell you that it's something iron or iron something, it's not enough information. There's not just one ion that iron can form, for example. When I ask what charge does calcium want to have, you tell me +2. When I say what charge does iron want to have, you say I need more information because it's in the D block area. If you look at question 3, starting with A, it says chromium 3 chloride. So chromium 3, what does the Roman numeral 3 tell me? Go ahead and finish writing it. Chromium 3 chloride. You think about that for a minute. What does the 3 mean? The 3 represents the charge, the amount of charge. It's a metal, right? So the charge is going to be a positive charge because metals want to get rid of electrons. You just don't know how positively charged it's going to be. In this case, it's saying chromium 3. So if we look over here for chromium, chromium is a column 6B element. We've just said that chromium wants to go to a +3, but it's in column 6B. That's why I said on that homework problem that the column headings don't tell you necessarily how many valence electrons they have. It only tells you how many valence electrons if it's an A column. A, 1, 2, 3, 4, 5, 6, 7, 8. The B columns, it doesn't help you. You can't look at the top of the B and go, oh, it has 6 valence electrons. No, it doesn't. Because these have multiple ions they can form. So chromium 3, it's telling me that my chromium, in this case, when I ask the question, what charge does my chromium want to have? I'm saying it's a metal, and the 3 tells me the value is going to be 3. So it's a metal, means it's going to go 3 positive. The chloride is a column element. Chlorine, okay? Chloride is an ion of chlorine. Chlorine is a column. It's 7A on the 3rd energy level. So chlorine, Cl, it always wants to form 1 negative. We have a metal, non-metal. It is ionic. We're good to go. Let's keep moving. Technique says chromium 1. We don't write the 1. Chlorine 3. Check to see if the charges match. 1 at 3 plus is 3 plus. 3 at 1 negative is 3 negative. Equal and opposite charges, we're done. And again, here, greatest common factor is 1, so that's good as well. Zinc 1 sulfide. I'm just going to put the shorthand down. Zinc 1 sulfide. Okay, so zinc, because it's zinc 1, we know it wants to have a 1 plus. Sulfur, we've already talked about, it's over on 6, so it wants to have a 2 negative. Metal, non-metal, it's ionic, we're still good. Transpose as subscripts, Zn2s, zinc sulfide. Check it. 2 at 1 plus is 2 plus. 1 at 2 minus is 2 negative. Equal opposite charges, and they're already at their greatest, or excuse me, you've already applied the greatest common factor to this, and so we're good. Zn2s. Titanium 4 phosphide. Titanium. Okay. I'm not going to look at where it is on the table because I have to look to the information, the Roman numeral. Titanium wants to have a plus 4 charge. See that? Because it has a Roman numeral 4 after titanium in the problem. I know that its charge value is going to be 4, and because it's a metal, it's going to be positive. So it becomes 4 positive. That's the ionic form of titanium 4. And phosphide. Phosphide is the Ide name for phosphorus. Phosphorus, symbol P. It is a column 5 element. Column 5 elements want to take on what ionic charge? -3. So metal, non-metal, we're on the right track. Transpose as subscripts, Ti3, P4. Greatest common factor, 1, so we're good. Check the charges. 3 times plus 4 is plus 12. 3 at plus 4 is plus 12. Here it's 4 at minus 3 is minus 12. Equal but opposite charges, we're done. Now we get to ordering some periodic properties. Yay! You either got this right or, I guess either got it right or didn't, right? What are the two options? But you either got it clearly right or you really struggled on this on the homework. So let's make sure we understand this. Order the following atoms in terms of their increasing ionization potential. Their ionization energy, ionization potential, same thing. What I would recommend you do is draw a little box like I did in class and say, okay, I'm talking about ionization energy. What is my trending for ionization energy? Up and right is positive. That's all you need to remember. Up and right is positive. Up and right is increasing. The question says, order the following in terms of increasing. So I'm going to start with the lowest one and go to the highest one. I'm going to start at the lowest and the farthest left and moving towards the highest and the farthest right. The elements are Sr, Ra, and Mg. Well, I'll go with one I can know off the top of my head. Here's Mg, right? I'm going to look and say, because this is first year chemistry, they're probably either going to put them all in the same row or put them all in the same column. So I have Mg, Sr, oh, look at there, and Ra. So I have 3 elements all in column 2. I have to put them in order of increasing. I've already reminded myself that going up is increasing and going right is increasing. So why don't I go up as increasing and say that they're going to be RA is less than SR, which is less than MG. Done. Yes, sir. If it says put them in order of increasing, you could have put them in commas, but I would have assumed that you understood that they were increasing as they went from left to right. This is much clearer if you put the less than symbols. This next problem has to do with the greatest desire to attract additional electrons. What are we talking about there? Electronegativity. Ionization is taking from, electronegativity is attracting to. What's the trend on electronegativity? Same thing. Same trend. GE, CA, and BR. Well, I know CA is here, right? I'm going to assume that they're either going to be in the same column or same row because, again, first year chemistry. Calcium here, put a blocker on that one. Calcium, germanium, and bromine. Bromine, germanium, okay? They increase from bottom to top and left to right. Hey, they're all in the same row, so we're just going to look in left to right. What's their order of increasing electronegativity? CA is less than GE is less than BR. Okay, just follow it across the row because the trend is positive, increasing going up and increasing going to the right. The third, number 6 here, says these 4 elements in terms of their increasing atomic radius. Remember that atomic radius is the counter trend to ionization energy and electronegativity. It goes the other way. So increasing radius is down and to the left as positive. It's the exact opposite of the other two. That is increasing. And so when they give us, again, 4 elements, I'm going to assume they're basically in either row or column: phosphorus, magnesium, aluminum, and argon. Well, phosphorus is over there as a column 5 element. Magnesium is all the way over here in the same row. Aluminum, yep, they're all in the same row. Phosphorus, aluminum, I'll write them over here. Phosphorus, magnesium, aluminum, and argon. So argon is my noble gas. It's all the way on the right in that row, right? So does it have the greatest or the smallest radius? Smallest radius, right? So it's going to be my smallest radius. Then as I move from right to left, let me come across and I'm bumping into next is going to be phosphorus, right? Do you see that? Now falling in the same row, I'm in phosphorus, continuing to the left. The next one I'm going to run into is aluminum. And continuing all the way across, all the way over to column 2 is magnesium. See, because I know the trend is from right to left, my radius is getting bigger. And since they're all in the same row, I just read them from right to left. Right to left is increasing radius. You could have put mg is greater than over here, you know, and doesn't do it the other way too. But if it says in here, order the following in terms of increasing radius, start with the smallest one and order them to the biggest one.